So last section we're going to look at, 2.4 part 3, okay, and it's on period changes. So we've looked at all the transformations so far, except this one. Okay, phase shift is when we move left and right. Vertical shift is when we move up and down. So we've done all the shifting. We've done one of the stretches. Okay, we've done vertical, stretching up and down. The last one we're going to look at is stretching or compressing horizontally. So, just like always, we got to look at what does the equation look like. All right, so I'm going to show you an example with numbers. That's what you're looking at right there. That is a period change. All right, so there's two things we look for. What's the operation we're doing? Right, is it adding or subtracting? Okay, then it's a shift. Or is it multiplying? If it's multiplying, it's one of the changes, either amplitude or period. Right? Now, with amplitude, you multiply by a number in front. With period, you multiply by a number inside the sine function, okay, right next to the x. So let's write that down. So, that says y equals sine or cosine, and then in parentheses, you're going to have something times x. Now, the something, you could represent it as any letter you want in math. When I give you an actual problem, it'll be a number. The book uses this letter that kind of looks like a W to represent the number that's in front of x. And that W, it kind of looks like a W, but it's actually a Greek letter, and it's omega. Okay, but omega just means that you're going to put a number in that spot, and that's what makes it a period change. Okay. I think yesterday when we did like amplitude, I might have used an A. For amplitude. The reason I don't want to use like P for period change, because we already had we had a phase shift. So we might mix them up if we use the letter P. So we just use something different. All right. So these are both examples of period changes. Sine 4x, cosine 2x, sine 1/2 x. Okay, they're all multiplying. But the difference is where? It's inside the parentheses. Okay. Even if you took the parentheses out, this is still the same thing. Same thing. So let's graph. Let's pick one of them and graph it. So I'm going to graph sine x, and let's graph sine 4x. Let's see what the difference is. All right. Okay, so we've got sine x and sine 4x. A little lazy, I'm not closing the parenthesis. The calculator doesn't really care. If you're going to do that, though, you really probably should close it. Right? But it doesn't matter on the calculator. Okay, so that's the original. And that's what happens if you do sine 4x. So what happened? If you compare the graph in blue to the one in red, what happened to it? Yeah. Yeah, it got smushed. Okay. So you got compressed. So let's make it a little bigger so you can see it better. Okay. Does anybody remember what number I put in? I did sine x and I did sine 4x. So let's look at the section from here to here. Okay. That's one cycle of the blue graph. If you look at it, it starts at the origin, up, down, back up. One cycle of the blue graph between those two green lines. Let's look at how many cycles of the red graph we've got in there. Okay. There's one, right? Up, down, and back up. There's 2. There's 3. There's 4. Exactly the same as the number that I put in front of the x. So what happened there is by putting 4 in front, it compressed the graph 4 times as much. Okay, and I'll show you what that sounds like in a little bit. Now, what do you think would happen if I change it from a 4 to like a 0.5? What do you think would happen this time?
It's going to stretch out.
Yeah, it's going to stretch it. So now the graph in red is going to be bigger. It's going to be stretched out horizontally. Okay, there's your There's your original. And there's your graph in red now. All right, you basically took the graph in blue, you stretched it out twice as much. Okay? You put a 0.5 in there, but what the decimal does is when it's less than 1, it stretches it. Right? So this one's kind of the opposite of what you would think. When you put in a small number like a decimal, small numbers actually make the graph stretch bigger. When you put in a big number, like a number bigger than 1, like 4 or 5, or if you put in like 100, the bigger the number you put, the more it shrinks. So this one is kind of like phase shift. It does the opposite of what you would expect. Okay, so now we know what we're looking for when we have a period change. Okay, you're looking for multiplication inside the parentheses. So, as we already said, you guys saw it on the calculator, period change is going to stretch or compress the graph along the x-axis. So there's two cases, right? It either is going to stretch or it's going to compress. I don't know if I exactly said it yet, but what kind of numbers do you think will cause your graph to stretch? Like, what do you think, like, the cutoff is? Like, if your number is bigger than this, you know, it's going to compress, but if your number is smaller than this, it's going to stretch.
Yeah, 1.
1. Okay, 1 is the cutoff between stretching and compressing. So you put a number in that's bigger than 1, you're going to get a compression. And you could do a decimal, like 1.5. That's a little bigger than 1, so that would cause a little bit of compression, not a lot. And if you plug in a decimal, like 0.5, 0.3, or a fraction, like 1/3, you're going to get a stretch. Now notice here, I'm never going to let omega, the number in front of x, I'm never going to let that go negative. We could, we just don't really get into it in this class. Anybody remember what happened when we had an amplitude change and we made the number in front negative? What did it cause the graph to do? Yeah, caused it to flip. Well, if I let w be negative or omega be negative, it would also cause it to flip. It would flip a different way. Just to draw something simple. If you had a graph like that, and you put a negative in front and we did an amplitude, it flipped over the x-axis. If you put a negative in front of the omega, so you did something like this, that negative would cause it to flip over the y-axis. So if I had, like let's just say I had a picture here, just going to sketch something like that, it would mirror image over here. It wouldn't flip down, it would flip over. So again, we don't really get into the having a negative in front of omega. That'll always be a positive number. And it'll never be 0. Never be 0. Alright, so let's just take a second and see if we can hear what that would sound like. Alright. So I'm going to take that program I had before. And when I stretched it or compressed it vertically, what did that do to the sound? Like when we did that yesterday. Yeah.
Change the pitch.
I don't think so. We stretched or compressed it vertically. It
Didn't it like change the area where you couldn't hear it?
you're thinking of like a phase shift. So that's what we did on Tuesday. Thinking back to Wednesday. Like if we played a sound like, like let's say you play a sound like this versus a sound like that. No stretch left and right, just a vertical stretch. That's volume. Like that's like the intensity of the sound, which we perceive that as a volume. Right? Louder, softer. So now, when we stretch and compress it the other way, we're going to talk about changing the pitch. So higher pitch, lower pitch. All right, so let's just kind of get a baseline here. I'm going to start with that. Not that loud. Okay. So that's a frequency that's 1,000 hertz. Okay. So remember, hertz means cycles per second. So that sound is oscillating up and down 1,000 times per second. And that's why it sounds the way it does. Right? If I had a speaker that was in front of you and I could show you, bless you, you'd actually see the speaker moving in and out 1,000 times a second. So you probably wouldn't even really see it. If we slow it down, then you might be able to see it. Okay. All right. So now let's go up a little bit. And I can play two different frequencies, but I just want to keep it on the same frequency. And notice in the picture, it started to compress. Okay, so the first sound I played was 1,000 hertz. Now this one is a little over 4,000. So it's higher pitch, definitely a lot higher, but it's still nowhere near like what the upper end of what we can hear. So let's try up around, that's about 8.6 kilohertz, okay, or 8,600 hertz, roughly. Okay. Now it's getting so squished together, the picture, it can't even really show it anymore because it's just so squished. It's still a wave though, but really squished. So getting a little higher pitch. Is there anyone that didn't hear that? Okay. So you passed your hearing test so far. So now let's go up to about a little over 12,000 hertz. Okay, it's going to be a much higher pitch sound. You also hear a little buzzing from the speaker. It's really just supposed to be the high pitched sound. It's just my speaker does that. Anyone that didn't hear that one? 12,000. All right, so let's go up to, let's try 16, that's about 16.6 kilohertz. It's a very, very high pitched sound. Didn't hear that? Yeah, I didn't hear that one. So at some point, you lose it. I mean, I hear something. I hear like my speaker going, but that's not really the sound. That's the speaker kind of freaking out. So, and then if we go even higher, let's go up to like, it'll probably be better if I turn this volume up and that volume down a little. So at 19.6, I don't hear that at all. I hear clicking. Well, I can't really hear because my door's open, but
yeah, I just hear your speaker.
I hear clicking, like this little popping sound. It's like every second or something, but I can't actually hear the sound that's making. Anybody hear it? If you heard it, it would be awfully painful. You wouldn't like it. I didn't hear it. So then if I start to bring it back down, like all of a sudden that crackling shouldn't happen, but start to hear it. Anyone hear it yet? A little bit. Now you hear it? Yeah. No, some people don't. So that's a really high pitch frequency. High pitch frequencies don't travel well. For example, if somebody's standing right outside that door, they're not going to hear that high pitched sound very easily. Now on the opposite end, like a low frequency, those travel well. Okay, you'll hear. Let's just start with something that's kind of low, but not super low. So it's a little over 600 hertz. So, I mean, it still sounds. Still sounds kind of high pitch, but I mean, compared to what we were just listening to, I mean, that was 600 hertz. We were listening to like 16,000, so it's a lot lower, right? Okay, that's lower. Now to do it accurately, I need to go over here and type it in. So my equipment has a point where it can no longer process the sound. Like if I go all the way down to 10, the wave is so stretched out, it almost looks flat, but it's not. It's still a wave. If I hit start, you can't even hear it. Because I don't have a speaker that can play a sound that low. Yeah, I can't. the lowest that my speaker can go is about, it's about 45 or 46 hertz. So if I play this one, you definitely hear it.
It's like a bean sub.
Let's put that rap to it.
Yeah. What I can do is, I can change that frequency just a little bit. And as I change it, there's different objects in this room that will resonate based on the frequency that's played. Kind of like you've ever seen, like if you take like a glass, right? And you just flick it with your finger, you'll hear that ping, that sound. That sound is the frequency that it resonates at. So if you did that to a piece of glass and you got the sound and you could play that frequency very loud, the glass would start to vibrate, and eventually if it was loud enough, it would break the piece of glass. So different objects in this room resonate at different frequencies. Watch what happens as I start bringing the frequency up a little bit. All of a sudden you'll hear like something start vibrating somewhere else, whether it's the lights or something. You'll hear it. It's not my speaker, that's the lights in the room, or something.
Kids in other class.
Now I can still count this is finally done. So, you started to hear that resonating, but if I change it back down to here, back where it was, I don't hear it. I mean, I hear the bass, but I don't hear whatever was vibrating, because that's exactly the frequency it vibrates at.
I need this in my car.
So, any questions on that? The different frequencies. Okay, so the idea when you stretch and compress horizontally, you're changing the pitch, okay, the frequency that you hear. Also, I've noticed that if I play with the high-pitched frequencies too long, like I've played with it a lot when I don't have a class in here, my ears start to feel very warm. Like they start to get hot, like almost inside my ear. And I think it's because my eardrum, even though I can't hear the frequency, it's vibrating my eardrum so much, it's like, it's actually getting warm. Even though I can't hear it. So, it doesn't feel good after a while. Alright, so, when you throw that number in front, right, like cosine 4x, by putting a 4 in there, you've changed how fast the graph is cycling. Right? You've changed the pitch of the sound. So what I want to be able to do is figure out what is the new cycle. Okay? What is the new period of the graph? Okay? Originally, what's the cycle been all week? We started at 0, and what was the last x value? 2 pi. Okay? It was always 0 to 2 pi. Now, to figure out the new cycle, you take the original cycle, which is 2 pi, and you divide it by whatever number you put in front of x. Okay. That will tell you how long your new cycle is. All right, so again, just to kind of show you visually, this is how it was all week. 0 to 2 pi was one cycle. Maybe if we compress it a little bit, maybe we do something like this. Now maybe the cycle is 0 to pi. Right? We've compressed it twice as much. So it's cycling twice as fast as it was before. And I showed you guys one where it cycled 4 times as fast. So this is how we figure out the new period. Take 2 pi and divide by the number in front. You got to do out this calculation right there. And t, I don't know why, but the book uses that for period. That's all. Okay. So these are going to be a couple problems where there's no graphing involved. Okay, we are going to do graphing, but not yet. We just want to be able to find the period of this equation. So sine 2x. So first of all, I just want to kind of think. I put a number in front of x bigger than 1. What happens to the graph when you put a number in that's bigger than 1? What does your graph do? It's going to compress. Compressing means that it's going to cycle faster. So I'm expecting to get a number here that's compressed or smaller than the original. The original would have been 2 pi. We should get a smaller number here, okay, because it's compressing. It's going to be faster. So the formula to calculate the period, it's always a fraction. And Courtney, what number do you always put in the top of the fraction in the t equals formula?
Pi. 2.
It's not pi, it's not 2.
The Greek letter.
So that's the bottom. I'm looking for this.
Then if it's not 2 or pi, I don't know.
Well, that's not a pi and that's not a 2.
360.
So, first you said put that, right?
Yeah.
Then you said, no, 2. So I said, okay. It's not a 2 and it's not a pi. It's a...
I don't know.
It's a 2 pi.
It's a 2 pi.
Oh,
You need both. Not just pi, not just 2, you need both. So 2 pi goes in the top. And for this one,
Let's just mess with that.
what number would go in the bottom?
2.
Yeah, the Greek letter, and in this case, that's a... No, we have a number for it. We've got to put a number in there.
Oh, 2.
2.
So it's just pi.
So in this case, the period is just pi. And that's what I just drew a picture of right there. Right? So I got a smaller number. The original period was 2 pi. This period is 1 pi. That means this graph is going to do its full cycle in a smaller amount of space than the original. This one needs 3.14 units. The original needed 6.28. So it's smaller, it's compressed. Let's try this one. What should happen here? Is this graph going to compress or stretch? Compress. More or less than the last problem? More. So now I'm expecting an even smaller number. Okay? Even smaller. So let's find the period. So the number in the top. Courtney.
2 pi.
2 pi. Here we go.
Yeah.
Wait, is it always going to be?
It's always 2 pi. It's the number in the bottom that changes. What's the number? That's the Greek letter. Okay, that's the number in front of x. So in this one, we got 2 pi over 5. If I could reduce that, I would, but I can't, so leave it. So that's basically 1/5 of the original cycle. The original cycle is 2 pi. You've divided it by 5. So this graph would cycle 5 times faster than the original. Okay. That doesn't correlate directly with sound. That doesn't mean the frequency would be 5 times as high pitch. I'm not sure the exact connection. But the graph itself would oscillate 5 times faster. Right. Questions on that one? Okay, let's try this one. Sine 1/4 x. Right, so Stephen, what's going to happen with this graph? Are we looking at a stretch or compress?
It should be stretched.
Should be stretched, yeah. It's going to stretch out quite a bit because this is a fraction less than 1. Okay. So let's find our period. So 2 pi always goes in the top. Anthony, what's going to go in the bottom this time?
Quarter.
Quarter.
1/4.
So we're taking 2 pi and dividing by a quarter. So if you want to think of it this way, it might be simpler. Maybe not. So you're dividing a fraction by a fraction. You've got 2 pi in the top. You've got a quarter in the bottom. How do I divide by a fraction? What do I have to do? Flip it and multiply. Yep. So we take, the top stays exactly the same. Take what's in the bottom, we're going to flip it. So we get 4 over 1. And we multiply. So what's going to be the period length of this graph? 8 pi. That's a way bigger number than the original. Okay, the original is 2 pi, so for this graph to do a cycle, it's going to have to go all the way from 0 to 8 pi. That's 4 times as stretched out as the original. Okay. So that would be a lower frequency sound, much more stretched out graph. Okay, any questions on that? Now, what if I took this graph and did that? 3 sine 1/4 x. What would be the period now?
Still a quarter.
Still, what did we get for the period there? We didn't get a quarter.
Oh, it was 8.
We got 8 pi. Okay. What does this 3 do?
Isn't that the amplitude change?
That's an amplitude change. So yeah, it changes the graph, but it has nothing to do with changing the period. The only number that affects the period is that number right there. That changes the amplitude. What if I did this? What would be the period now? Yeah,
Still the same.
it's still the same. Just because you shifted it up, that doesn't mean you stretched it out anymore. You just moved it up. Okay? So I'm going to give you ones like that on the test, not to graph, because we haven't practiced graphing multiple transformations in the same problem. But I would give you one like that and say, what's the amplitude? Or, what's the period? Okay, so you have to know which number to focus on. And a lot of people, when they look at this, they say, oh, the period is 1/4. No. 1/4 is just the bottom of the fraction. Okay? It's 2 pi over 1/4. Okay? Same thing here. Don't say that the period is 2. No. Period is pi. Okay? 2 is just the number that goes in the bottom of the fraction. Okay. So any questions on that? All right. So by knowing this number, that's important because we now know where the graph ends. This tells you the length of one cycle. Here's a picture of one cycle. If that's where the cycle ends, then that number is 8 pi. Okay? So when we get into the graphing, we're always going to start at 0. And then we're going to first figure out where does the graph end. Well, it ends once you finish one cycle. How do you know when you finish one cycle? Use the formula for t. That'll tell you the end of one cycle. And then if you know the beginning and you know the end, how do you think you could get what's exactly in the middle? Yeah?
Add them up, divide by 2.
Yeah, and that's all we're going to do to figure out all the other ones. We're going to average, and then we're going to average, and then we're going to average. So it's that easy to find all your x coordinates. You just find the beginning and the end, and then you average to get the middle, and then average again and again to get the other two. Okay, I'm gonna write that down. But that's basically what we're gonna do. All right. So, how do we modify our original table? Okay, so now we are stretching and compressing horizontally. So that means which values are going to change? Which ones? Only one. Yep, every transformation this week is only one. I'm not going to give you one where two change in the same problem. Yep. Just the x's. Okay? All you're doing is stretching and compressing horizontally. Go back and look at this picture. Focus on like the height of the wave as I stretch and compress. Okay. As I stretch and compress, there's no change in the height. Things are just stretching and compressing. So all we're doing is changing the x's. Unfortunately, that means the y's stay the same. The reason I say unfortunately is because the y's are the easy numbers to work with. Those are the ones and zeros. We don't get to work with the ones and zeros today. Okay, so we're going to copy the y's down from the original table. You're going to have to work with all the x's. Those are all the fractions with pi. Okay. But it's not too bad. Now, every graph that we've done, the first x value whether it's sine or cosine, has always been what number? 0. So let me ask you, if you take 0 and you stretch it, like say you multiply it by 3, stretch it out 3 times as much, what do you get? 0. What if you take 0 and compress it? Like take 0 and make it half as big. What do you get? 0. So because we're always going to be starting at 0, no matter how you stretch or compress 0, it doesn't matter. The first x coordinate is always going to be 0. Now, if you ever do this kind of thing in the future, and whoever you're doing it with does multiple transformations in the same problem, that will not always be true. The first x coordinate might not be 0. Like if you did a phase shift and you shifted everything to the right, and then you did what we're learning today, you wouldn't be starting at 0 anymore, because the phase shift would have moved you to the right. We're not going to worry about doing 2 things in the same problem, so that's never going to come up on the questions I give you. Okay. So that's the beginning. The first x coordinate is always going to be 0. Then we have to figure out where the end of the cycle is. Okay? Because the goal is to figure out the beginning and the end, then we can get the middle. Okay? So the 5th point on your graph is the end of your cycle. How do you find the end of the cycle? That's what I just showed you. It's the t equals 2 pi over omega formula. All right, so now you got something like this. You get the beginning, you've got the end. And somebody told me earlier, what did we do? What was the word to get the one in the middle? You take those two and do what? Follow Justin. So how would you find, like if you knew the beginning and the end, how would you find the one that's evenly spaced between the beginning and the end?
Well, I would just divide the one in the end by 2.
Okay, so you're averaging with 0, which really means you just have to take half of it. It's like if you had 100 for a test grade and you got a 0, well now you have a 50 average. So all you really have to do is divide by 2. So really you're just finding an average. Just finding what's in the middle. So we're going to average. So to get the 3rd coordinate, which is the one right in the middle, it's the average of the 1st and the 5th. Okay, so here's the 1st, here's the 5th. Now you've got the 3rd one, right in the middle. Remember, we're going to have 5 when we're all done. So now you know coordinates 1, 3, and 5. How do you think you'd get coordinate 2? Keeping in mind that everything is evenly spaced. Oh, Jason. All right, so if you have 2 numbers and you want to know what's exactly in between them, what do you do?
By 2, what you did, finding the first one.
Yeah, we're going to do the same thing again. We're going to add these 2 together and divide by 2. And that will give you the 2nd coordinate. Okay, just add them up and divide by 2. All right, so now we've got the 1st, 2nd, 3rd, and the 5th. Brianna, how do you think I'm going to get my last coordinate, which is the 4th one? Divide by, yeah, we're going to add them up and divide by 2. So we're going to average the 3rd and the 5th coordinates. Now, there's other ways to do this besides averaging. We're using averaging because we're taking advantage of the fact that everything is supposed to be equally spaced. And when you find an average, it gives you a number that's exactly in the middle of 2 numbers. This method is not always the best way to do it. Depends on the problem. But, so I don't confuse you, I'm not going to show you like 2 or 3 different ways to do it. Okay, this method will work all of the time. It's just not always the fastest. but it's pretty simple to understand. Okay. Any questions on that? All right, so let's try a couple period change graphs and see what we can do. All right, so now we know all the graphs. Okay, we've got both the shifts, we've got both the stretches. So now we've got to be able to look at that and identify which one of the four that one is. Okay, so we're doing period changes, so it's a period change. But who can tell me why that's a period change? Yep.
Because it's in the function.
Can you be more specific?
I don't know, like it's just in the sine function, like it just.
So I'm looking for two things specific. I think you said one of them. But I'm looking for one other thing. Yeah?
Because the 2 from the x.
Okay, can you elaborate on that? I don't understand what that means. That's all you got. Yeah?
Because you're multiplying it.
Yes. When you put a number in front of a letter, it means multiplication. So two things, we've got multiplication, and it's inside the function. It's not multiplying outside. Okay. That's how we know it's a period change. Okay, so now that we know that, let's make our table. For a period change, what stays the same?
The first quarter.
Which ones?
The first quarter.
The choices are your x's or your y's?
Oh, the x.
Nope. So then it has to be. There's only one other option. The y's. So the y's are the ones that are going to stay the same. Okay? Because we are not moving up and down. We're not stretching up and down. We're stretching left and right. So what are my y values from the sine table? And they're different from cosine.
0.
Yep.
1. 0. Negative.
Yes. Okay, so we've got our y's. We get 5 points for that part. Now the first x coordinate we shouldn't think too deeply about. What did I say the first x coordinate always is? Yep.
0.
It's always going to be 0, because no matter how you stretch or compress 0, 0 is always 0. At least what we're doing. And now we want to find the end. So what's the formula to find where this cycle is going to end? And then I'll have the beginning and the end, and then I can start getting stuff in the middle.
2 pi over omega.
Yeah, so it's 2 pi over, what number is omega in this one? 2. It's the number in front of x. We did that problem earlier when we were just practicing finding the period. That's a period of pi. And now we're just going to keep averaging to find all the ones in the middle. What's the average of 0 and pi? Yep, pi over 2. What's the average of 0 and pi over 2? Pi over 4. See, averaging with 0, that's easy because you really just have to take half. Now, let's do this one, but we're going to do it off to the side. Okay, we're going to average pi over 2 and pi. So what are my steps to do an average? I got to take those two things and do what? Yeah. Add them up. Okay. So pi over 2 plus pi. And is that it? Is that the average?
You divide by 2.
Yeah, divide by 2. Do you agree that's the same as just taking half of it? Yeah, same thing. So I'm just going to add them up and then take half of it. Or divide by 2 if you want to say it that way. Okay, so let's do that and see what we get. Just need some more space. What's the problem inside there if you want to add those up? You want to add pi over 2 and pi together. Yeah.
They need the same denominator.
They got to have the same denominator. Can you tell me what my common denominator is going to be? Yep. So what I'm going to do is double the bottom, double the top. Okay. What's pi over 2 plus 2 pi over 2? 3 pi over 2. Now multiply straight across. 1 times 3 pi, 2 times 2. 3 pi over 4. Now, if you look at those x values, just read them in your head going down. It doesn't really look like there's a pattern. But there is a pattern there. Think of this one as 2 pi over 4. Think of this last one as 4 pi over 4. It's the same thing, just we have all the reduced versions. 0 pi over 4, 1 pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4. If I had to keep going, 5 pi over 4, 6 pi over 4, 7 pi over 4. So there is a pattern there. Any questions on the pattern I just showed you or how I got those numbers in the table? Okay, I think fractions with pi, it's hard to see patterns. If these were degrees, you'd see it no problem. 0, 45, 90, 135, 180. It's plus 45 each time to get from one to the next. Right. So since they are all equally spaced, we can just use those as our labels on our axis. So let's go 0, pi over 4, pi over 2, 3 pi over 4, and pi. Now, when you put your labels, you don't have to have all the same denominator. You can do labels like that. That's fine. Should probably try to move these a little closer, but kind of ran out of space. All right, so 0, 0. We got pi over 4, we're at 1. Pi over 2, 0. Negative 1, back to 0. And there's our graph. Any questions on the sketch? Okay, if you're looking at it like you said to label everything and I didn't label the y-axis there, that's technically okay. If you don't put labels on marks, I'm going to assume you're going by ones. That's what people always assume. If you look at a piece of graph paper, each line is 1 unit, unless you label it otherwise. So if you leave these off, it's fine. If you put these in, it's still fine. If you leave these off, it's not fine. If you leave those off, I'm going to assume that that's 1, 2, 3, and 4. And your graph definitely doesn't end at 4. It ends at pi. Questions on that one? All right, let's try this one. So cosine 1/4 x. Now, I don't specifically ask you on the test, like, what kind of transformation is this? Sometimes as people take the test, they write it down, like, oh, period change or vertical shift or whatever it is. So if it helps you, you can write it down. But all I'm really looking for is the table and the sketch. Okay, so now, what kind of transformation is that one?
It's a period change.
Yep, it's a period change. And can somebody tell me why? See if we can get this time. Yeah.
Because what the numbers on the inside of the parentheses multiply. Yeah.
Inside, multiply. Those are the two things he had to say. Multiply inside. Right? Multiply outside, different story. Okay. But inside makes it a period change. Y's stay the same. Megan, anytime I do a period change, the first x value is always what? 0. All right. Now, after I get the first coordinate, what's the next one I get? The fifth one. I'm going to jump down to the last one. Remember the formula to find the fifth one is 2 pi divided by 1/4. We already did this earlier. What did we get when we did 2 pi over 1/4? We got 8 pi. Now, just because of the way the numbers work out, the averaging here is going to be super, super nice. What's the average of 0 and 8 pi? 4 pi. Average of 0 and 4 pi? 2 pi. Average of 4 pi and 8 pi? 6 pi. And it's really easy to see the pattern there. 0, 2, 4, 6, 8. There you go. That's it. That's your table. Questions on that? All right, so let's plot those points and make our sketch. 0, 2 pi, 4 pi, 6 pi, 8 pi. So this graph technically should look way stretched out, but it's not going to. Why isn't my graph going to look like huge across my screen right now? Because of the way I labeled it, right? I changed my scale, right? I didn't go 0, pi over 2, pi, 3 pi over 2. I mean, if I did that, I'd be on the hallway with my graph. Okay, so I went 0 to 8 pi to make it fit. 1 and negative 1. Okay, now plot our points. 1, 0, negative 1, 0, 1. There's your sketch. Okay, any questions on that one? Right, I think we got one more and that's it. Now, at first, this one looks bad, right? It looks like we got this crazy number in front of x this time. Pi divided by 2. Well, pi is 3.14. If you divide that in half, that's about 1.57. So this is a little bit of a compression, right? Number's bigger than 1 compress. But it's not much. 1.57, barely compressing it a little. Right? So again, it is a period change for all the reasons we've said several times. So let's copy our y's. Okay, Anthony, what's my first x value?
0.
0. And can someone else give me my formula to find the last x value? 2 pi over omega. What's omega this time? Yeah, so I'm going to write it like this. 2 pi, okay, 2 pi over 1, same thing. Just if I have a fraction in the bottom, I like to have a fraction in the top. I like to keep everything the same. Either keep it all fractions or keep it all without fractions, but this one has fractions. Now, how do I divide those two things?
You flip the bottom.
Yep, flip the bottom one and multiply across. 2 pi over 1 times 2 over pi. What's that going to give me when I multiply it out? 4 pi over pi. The pi's basically cancel. And all we're left with is 4. So this is going to be the first time we've had a problem all week where the x values aren't going to have pi. They just canceled out. What's the average of 0 and 4? 2. 0 and 2. 2 and 4. Okay, done. So technically, I don't have to label anything on that graph. I want to go by ones everywhere. I really want ones. I want this to be 1, 2, 3, 4. I want that up there to be 1, and I want that to be negative 1. So this is the only problem all week. If you leave all your labels off the graph, you'd be fine. So we got 0, 0, 1, 1, 2, 0, 3, negative 1, 4, 0. And that's your sketch. Okay, so sometimes you look at it at first and it looks like it might be real bad because it's got pi in it already before you even start. But then somehow the pi cancels out and it actually makes the problem come out very nice. Okay, so any questions on that? Okay, so what I'm going to do, I'm going to try to show you a couple things. I'm just going to pause, wrap up the video, and then I'll show you something. All right, so homework tonight will be a worksheet on the period change. And don't forget, I will be after school today, and we have our test tomorrow.